Thank you so much. Let me start by saying what the talk will be about. So this will be about a geometric representation theory proof of a mild version of the Beauville-Voisin conjecture for Hilbert K3. So I will say a bit more precisely what this is a bit later on, but this is a result that, let's say the statement here. So the statement is that the cycle map A star of x to H2 star of x is injective on the subring of A star of x generated by tautological classes. I'll say what these are in a second. Notation-wise, A star of x denotes CH star with coefficients in Q, but I'm writing it as A star because, you know, the whole point of this talk is about the distinction between Chow and cohomology. So I want to use very differing notations for these two things. Now, the particular result over here, the injectivity on the subring generated by tautological classes, is not in itself a hard result. And even though I haven't seen a proof of this fact in the literature, I would not be surprised if some people could know, probably even some people in this audience, could know how to prove this fact. The reason why I'm talking about it is actually twofold. So first of all, I want to focus on a representation theory part. So the proof uses a representation theoretic argument, which I think is neat. So let's say here, a neat rep theory proof. Well, you will be the judges of whether it's neat or not. But I will do my job of actually showing you what the proof is at the end. So, well, I'll sketch the proof, which is the best you can hope for in a talk nowadays. This, I think, is a good way for representation theory to drive home an argument. But a bit more seriously, I would say that what we do is it is worth it because in the process, we lift a number of formulas. So we lift some formulas of Lehn and Li-Qin-Wang from cohomology to Chow. So in a certain sense, we can prove some formulas about the intersection theory of Hilbert schemes of K3 surfaces from cohomology to Chow. And I should say, before I go any further, I should say who we are. So this is all joint work with Davesh Maulik. And this, in a certain sense, is the plan of this talk. Okay, so I should start by talking about K3 surfaces, which I will do very briefly, especially since they were discussed yesterday. But I have to do my, it's my duty to say that let S be a K3 surface. Everything is over C. And we want to study the Chow groups of the K3 surface. Well, as all Chow groups are, well, it starts with A0, which we understand. Then you have A1, which more or less we understand. But then you have A2 of S, which is really, really big. So this thing is very, very big. Now, the cohomology of S, on the other hand, is also something we understand. H0 of S is down here, H2 of S is over here, this is one-dimensional, this is 22-dimensional, and this thing is also one-dimensional. So when you have the cycle map, which I will call zeta for lack of better notation, it goes from Chow into cohomology. You immediately observe that you have something very big here, something extremely interesting, mapping it to something one-dimensional. So the upshot of this is that zeta is very far from being injective. I mean, it's also not surjective, but we kind of understand the how far it is from being surjective. It's a question of whether cycles are algebraic or transcendental. But the injectivity of zeta will be the main focus of my talk. All right, so it's certainly not injective because you map something very infinite into something one-dimensional. But how can we salvage this? Well, we have already seen yesterday in Yin's talk, we've already seen a very important property of Chow groups of K3 surfaces, namely the following relation, the fact that there exists a special class, which I think he called CX yesterday, but I'm going to call, I think he called CoX yesterday, but because I want to confuse you as much as possible, I'm going to call it C. You're going to see that a lot of the annotations will be adapted. So there is a class C in A2 of S with the property that for all Visor classes, so for all L and L prime in A1, we have the product of L with L prime, the product in the Chow group, is a multiple of this class C, and the multiple here is just the intersection pairing of L and L prime, which, because everything is done over Q, it's going to be a rational number. So the upshot of this is that whatever things in A1 you multiply, you end up in multiples of C. And this is a very special property that is only true for K3 surfaces. I think it goes back to Beauville-Voisin, but feel free to correct me if I get the history wrong. Well, the upshot of this for us is that R of S, which is defined as A0 of S plus A1 of S, plus the multiples of C, is a subring. So this thing is a ring because it's closed under the cup, it's closed under the intersection product. And now this thing is of the size we want. The A2 part, instead of being the whole infinite dimensional thing, has become one-dimensional. So in the case of RS, the restriction of the cycle map zeta to RS will be injective. So the moral of this board here is the following. The cycle map on the whole of Chow is not injective, but there is a subring, R of S, which contains all the Visor classes, such that the restriction of zeta to this subring is injective. And this is kind of nice because you care about the injectivity of zeta for the following reason. You want to be able to say when two cycles are equal. This says that two cycles are equal if and only if their images in cohomology are equal. And this is true for cycles which are in this subring. Put differently, if you want to prove an equality of cycles in RS, essentially what this is saying is that you can take Kunez components, which is something you cannot do in Chow per se, but you can certainly do in cohomology. So knowing this injectivity helps you a lot in understanding cycles in RS. All right, how to generalize this? Well, this is a surface. You want to generalize this to higher dimensions. The setup is when S is replaced by X, as we saw yesterday. This is a holomorphic symplectic variety. I should call it an irreducible holomorphic symplectic variety. Holomorphic symplectic variety. Okay. Then you want the generalization of this problem is to find a certain subring R of X inside the Chow of X, which injects into cohomology. And you want it to contain some interesting classes. You want it contain stuff as divisor classes and Chern classes of the tangent bundle. And actually in the case which I'm interested in the case when x is equal to the Hilbert scheme of points on a surface, when x is equal to Hilbert of S, you will actually want it to contain Camorra classes. So this is the name of the problem, find subrings of Chow which inject into cohomology, and I will be more specific about what this problem is saying in the case of Hilbert schemes. The case of Hilbert schemes is the only one which we will encounter in this talk. So S is also a K3 surface as before. We are considering the Hilbert scheme of n points on S. Because S will be fixed throughout this talk, I'm just going to call this Hilbert. And remember that this is the algebraic variety which parameterizes ideals curly I inside OS such that the length of the quotient is n. Everything is over C, so there's no worry about the notions I'm writing down here. So this is the ideal of a subvariety of n points, or n add points on the surface. So we're interested in the Chow groups of this. What kind of interesting classes in the Chow of Hilbert schemes one can write down? Well, you have quite a big family of classes, and they all stem from the fact that Hilb n of S has a universal subscheme. So let me recall that the universal subscheme, I will denote it by Zn. It's, well, you can think of it as a subscheme or as a family, so because of that I'll put an arrow from Zn to Hilbert times S. This is, well, very coarsely, Zn is just the set of pairs ideals and point such that X is inside the spec of the quotient. So X is a point in the subscheme that is determined by I. Because of that, Zn is actually a subscheme of Hilbert times S. I'm writing it in this way because this is the moduli theoretic understanding of what this family is. But over here on Hilbert times S, of course, you have two maps, one of them in Hilbert and one of them to S. Let's call this pi1 and this called pi2. And I claim that we can use this diagram to obtain a lot of interesting classes in the Chow groups of Hilbert. So how can we do that? Well, you can always take, any polynomial in the Chern characters of the structure sheaf of this subscheme. So this object is something in the Chow of Hilbert times S, because you multiply the Chern characters of a certain sheaf on Hilbert times S. You can push that over to Hilbert, and that will give you classes in the Chow groups of Hilbert. But before you do that, actually, you can also multiply by things that are pulled back from S. So you can always multiply here by pi to upper star of gamma for any gamma in the Chow of S. So I claim that this actually gives you a big family of classes in the Chow groups of Hilbert, and they are extremely interesting. For any polynomial and any gamma, you take such a class, and then you can take these classes on Hilbert and multiply them together, form polynomials out of them, so you actually get quite a big ring over there. So, for example, the Chern classes, the Chern character of the tangent bundle to Hilbert is of the above form, where the polynomial is a certain quadratic polynomial. So the form above for some quadratic polynomial. Unfortunately, it's not the case of quadratic polynomials, which I will be studying in this talk. I will be studying the case of linear polynomials. So the definition I want to give, the things which I call tautological classes, are the following. So a tautological class, in my terminology, is of the above form. So it is pi1 lower star of a single CHK of OZN times pi to upper star of gamma for gamma which is only allowed to be in this particular subring car of S. So I'm giving here a kind of restricted definition of what tautological classes are, in that I only allow gammas in that small subring, and I only allow linear polynomials in CHK of the structure sheaf of this subscheme. So that is a definition of a tautological class, and because of that, the weaker version of the conjecture which we prove is that the cycle map from the Chow of Hilbert to the cohomology of Hilbert is injective on the subring generated by these tautological classes. So this subring actually contains all the visor classes, but it does not contain the Chern classes of the tangent bundle, because as we've seen in this remark, the Chern classes of the tangent bundle require using quadratic polynomials in this universal subscheme, whereas in our definition we only have linear polynomials. So the upshot, the hope of this talk is to, let's give a representation theoretic proof of this result.
So Chow 0 of a vector bundle, I guess, is the rank. Here is generically 0.
Exactly.
But you can think that maybe you can. So what about just not using this Chow at all? So just taking pi 1 lower star, pi 2 upper star of gamma. So this is not, in your definition, it is not a tautological class.
Nope, it's not a tautological class. That's a very good point. So let me actually write down a few of these. I was going to at some point, and I think it's a good moment now. So CH0 of OZN is 0, as you mentioned. CH1 of OZN is also 0, essentially because ZN is a codimension 2 subscheme. The first interesting one, well, the first trivial one, I should say, is CH2 of OZN, which is just the cycle given by the universal subscheme Zn itself. And the first really interesting one is CH3. So I'm not going to say what it is right now. I'm not sure I could say anything other than saying that it's CH3. But this is interesting, and I will give you some formulas for it. Interesting. And then CH4 and so on become more and more complicated. So in particular, as you asked, well, what is the corresponding thing with the one here, a tautological class? I guess the answer is no. But then I also guess that maybe it's not so particularly interesting because it's a constant. So
yeah, because
yeah, you can boom, and you can just integrate on S.
So it is maybe.
I guess. Well, in general, it will be 0. If gamma has degree 2, it's going to be a constant. So because of that, I'm not going to think about it. The reason why we use this particular normalization for tautological classes, so the reason why we put here CH instead of Chern polynomial or something else, is that in the formulas of Lehn and Li-Qin-Wang, which we extend from cohomology to Chow, the formulas are naturally presented in terms of Chern character. You could probably not get a nice formula for, say, if you put the Chern class Ek in here. Especially since the Chern class is a non-trivial polynomial in the Chern character, so it doesn't really fit in well into our theory. Okay, so I should say I'm very sad to be pessimistic, but unfortunately I can even show you how representation theory fails to generalize this result to the setup where you generalize tautological classes by using arbitrary polynomials instead of just as linear polynomials. So I will show you a proof of a result I have on the board. I probably won't have time to, but it's also quite possible to explain why such a proof could not extend to the case of more generalized tautological classes where you allow arbitrary polynomials in the Chern characters as opposed from just linear polynomials. Oh. No, I'm sorry, I moved that out, but whatever. All right, so where does representation theory start? So what does representation theory have to do with all of this? Well, it all started, say, 20 years ago with the work of Nakajima and Grosznowski. So let us recall the construction, the Heisenberg algebra action, due to Nakajima and Grosznowski. So just like everything which I call representation theory in this talk, it's actually intersection theory, but it's presented in a representation theoretic language. So it actually has a very strong intersection theoretic flavor, because their construction starts by saying, consider the locus. So you have here, say, your Hilbert scheme of n points, and you have here the Hilbert scheme of n plus k points, where n and k are arbitrary numbers. And you want something, you want a subvariety which, well, involves both of these Hilbert schemes. So what they defined is something which I will call Hilb n plus k. So this now is a set of not just a single ideal, like Hilb n and Hilb n plus k, but it's going to be the set of pairs of ideals. And actually, I will even take pairs of ideals together with an extra point. So let's write I, x, and I prime, such that, well, you know, I is a point in Hilb n, x is a point in S, and I prime is a point in Hilb n plus k. What interesting things can two ideals and a point do? Well, one ideal could sit inside the other. And, you know, if one corresponds to Hilb n and the other one corresponds to Hilb n plus k, this is the only way they can be contained inside each other. And you can ask for the support of their quotient to be concentrated at one point, namely the point x. It theoretically supported at x. Of course, you could have relaxed this condition here, but prescribing a certain partition of points corresponding to a support naturally boils down to just considering these loci and their fiber product. So in a certain sense, you can think of these loci as being the building blocks of the set of pairs I and I prime, which are contained inside each other. So what do these things mean for us? Well, this is you can think of the thing on top as being a cycle. It's a singular algebraic variety. It has projection maps to Hilb n, to S, and to Hilb n plus k, which remember these two ideals and the point. Let's give these things names. Let's call this P minus, PS, and P plus. And now that you have, you know, a space and your Hilbert schemes and a bunch of maps in between them, you can construct interesting operators on the Chow groups, and this is what these people did. So define.
So the support equal to x, is it in the set theoretic?
In the set theoretic way, yeah. I mean, the quotient over here will be a length k subscheme supported at the single point x. So it will be a fat point.
Okay, so then to define it scheme theoretically, you need to do something.
I'm sorry?
Too much. To define this scheme theoretically, you have to do something.
Oh yeah. You certainly have. It's not immediate. For the purposes which you will see here, I only need to define a cycle. And if I'm defining a cycle, I can always say something like, well, it's the closure of a certain open locus, and there's a certain open locus which corresponds to subschemes that are so-called curvilinear, meaning that they are contained in a smooth curve, and you can probably define those in an easy way. So your objection is true, and you can define this, but for the purposes of the definition now, all I will need is a cycle in the product of two Hilbert schemes. Well, you know, I'm just saying that same thing in a number of ways. The thing which I really want to define is that you want to define for any class gamma, a priori in the Chow group of S, but ultimately we will just be looking at R of S. So for any Chow class on S, you can define the following operators. So these will be operators on the cohomology of Hilbert schemes. So here you have Hilbert and Hilbert plus k. N will be arbitrary here and will not play any role, as you will see in a second. There is an operator called qk of gamma, which goes from here to here, and there's an operator called q minus k of gamma, which is going back. And they are defined by using this correspondence here and pullbacks and push forward maps along these arrows. All of the maps here are proper, so we don't have to worry about push forwards. And with pullbacks, well, there are a number of ways to define the operators. I will not be going into them. But the formula for these operators are the following. Qk gamma is p plus lower star, ps pullback gamma times p minus pullback. And q minus k gamma is the same thing with minus and plus swapped and a sign in front. So these are the formulas. And if you think about it, they're not so unnatural, because ultimately, if you want an operator from Chow of Hilb to Chow of Hilb, and all you have in the world is this diagram, pretty much the only thing you can do is pull push, and then you can feel free to multiply by some classes pulled back from S. So this is kind of the only natural thing that you can do. As you may observe, there is no n in these formulas, so we can alternatively, we may think of q plus or minus k as operators on the Chow groups of all Hilbert schemes of arbitrarily many points. So we will think of q plus minus k gamma as endomorphisms of the following very, very big group. And this is actually fundamental to the construction of Nakajima and Grosznowski, endomorphisms of the following really big abelian group, A star of Hilb, which is going to be the direct sum for all n going from 0 to infinity of A star of Hilbert. So essentially, a philosophy behind the statement I'm saying here is, if you're constructing operators which go from one Hilbert scheme to another, you might as well study all the Hilbert schemes together. It's more beneficial. And historically, interest in this construction started from when these people used this particular construction to explain the formulas for the Betti numbers of Hilbert schemes, which had been discovered, I think, in the early 90s, and they were explained representation theoretically exactly by this construction, for which it is fundamental that you study all Hilbert schemes together instead of independently. So the representation theory here is only a tool, and it's only a way in which we can study his operators, and we can make this precise by saying that the theorem due to these people, Grosznowski and independently Nakajima, is the following. Well, in words, I will say that the operators q plus or minus k, well, let's just say qk and let k be an integer. So these things where k goes over the integers except for 0, and gamma goes over all classes in the Chow of S, these things give rise to a Heisenberg algebra action on the Chow of Hilbert schemes. And if you don't care so much about Heisenberg algebra actions, or even about the defining relations in the Heisenberg algebra, I will spell out what this means. So i.e., this is just words for saying that the following relation holds. If you take the commutator of qk gamma with qk prime gamma prime, these two operators have a very simple commutator. It's almost always going to be equal to 0. The only time it will not be 0 is when the indices are opposites of each other, so when you have qk and q minus k. And in that case, you will get a multiple of the identity, and the multiple is precisely this thing. So the representation theoretic meaning of the result is that, look, the operators they constructed satisfy these very simple commutation relations. And these very simple commutation relations are just a representation theoretic way to encode the intersection theory of Hilbert schemes and of these nested Hilbert schemes, Hilb and n plus k. Any questions about this? It's all of it is pretty classical stuff in geometric representation theory. There is a slight generalization of this, so I will leave it as an exercise for whoever is interested. So for any class now gamma in the Chow of not a single surface S, but of a product of T surfaces S, you can define the following operator. You can define analogously, I'm just going to write the word analogously here because I don't want it to be a scary construction, analogously, an operator which you can call QK1 QKT of big gamma, and this is also going to be an operator from A star Hilb to A star Hilb, and you can do so for any choice of indices K1 through KT. So what I'm saying here is following. His class here, gamma, is just a label on the operator QK. What I'm saying is that when you take a composition of T such operators, you can naturally label them not by classes in the Chow of one surface, but by a class in the Chow of a product of T surfaces. And, I can tell you how this is done in words. If you take QK1 times QKT, you can think of this composition in intersection theoretically as a fiber product. If you take a fiber product of T of these correspondences here, they will naturally map not to one copy of S, but to T copies of S. So then you can always pull back a Chow class from con ST and use that to run the exact same definition as I'm running here. The upshot of this is a single operator with a single integer carries a label in the Chow of a single surface. A composed operator with T indices carries a label in the Chow of T copies of the surface. That's the principle here. If anyone has any questions about this, I may regret going too fast afterwards because I may finish early, but then again, I can imagine the people at Get Lunch will be grateful.
When you write this operator, so where are the
this operator?
No, the last analogous one.
Over here.
Yeah, so the star, what is the star and the...
The star just means the Chow groups of ST, and I'm writing star because I want to say that they are graded. That's a very good point. Okay. So it goes from N to N plus K1 plus ... plus KT. A usage of a notation Hilb essentially for the disjoint union of all of these Hilbert schemes is like an artifice to not have to write these indices every time. But indeed, if you want to be careful and write the indices, then you go from Hilb anything to Hilb that something plus K1 plus K2 plus KT.
And why you write the notation GK1, GKT, and not just G is K1, K? I mean, what is the
operator here? Well, it was supposed to be a Q, but that's just my fault. So this is okay. I think I have time, so I'll say a couple more words. So what you really should be thinking about here, I'm not one to tell people what they should think, but the nice way of thinking about these operators is not as endomorphisms of a Hilbert scheme, but one really should think of QK as a homomorphism from the Chow of one Hilbert scheme to the Chow of some other Hilbert scheme times S. So this thing here is a natural way to encode all of these operators which I'm writing here. Now if you take this particular operator and you compose T such operators, if you do QK1, QKT, well, you can't really compose them in the trivial way because they don't go from the same group to the same group, but the natural choice for the composition of these things is going from Hilb to Hilb times S times S times S, T copies of S. So once you have his operator, then I claim it's obvious how to get an endomorphism of A Hilb. Just take his operator, multiply it with the pullback of gamma from these factors and push forward. So that's essentially what is happening here, but in my attempt to write as little as possible, I clearly failed. I personally like his notation more, but classically a lot of this stuff was done in this notation. So this is also, I attempt to be a little bit historically accurate.
So can I ask, so if you allow the capital gamma as cycles, you get more operators.
Oh yeah, a lot of operators.
But is the structure known? I mean, if you go to this more general setting, is the structure of
So there is a result called De Cataldo and Migliorini, which say essentially that when n is large enough, so when you send n to infinity, the additive relations between these operators are exactly the same as the additive relations in the Chow of ST. So talking about an identity in the Chow of ST between gamma and gamma prime is the same thing as talking about this identity of operators when n is large enough. So here are two formulations of the same thing when n is really big. Well, in this case, I will only use very particular choices of gamma, but what you said is a very good point. You get a lot more operators here than just by composing operators from here, because you have a lot more classes big gamma than just exterior products of small gammas. Anyway, like I said, the first example of such an interesting composition in quotes, which I want to show you, actually happens when t is equal to 2. So, well, for example, you may take the following operator. You may take an operator which people call L sub k. This is also going to be an endomorphism of A Hilb. Pretty much all of the operators I will write in this talk will be endomorphisms of A Hilb. And this is defined in the following way. So it's a particular combination of products of these operators when t is 2. So what you do here is you write QA, QB. To make this into an operator, I have to feed inside here, well, a class in the Chow of S times S, and the particular class you put here is this so-called delta transcendental, which I will tell you in a second what it is. Of course, K is here and A and B are here. You have to sum over all K and B which add up to K. And the sum actually does go over all integers. So this is kind of natural because the algebra generated by these operators is naturally graded by the sum of all of the indices which you see. So if you write L sub k, it should be given by operators whose sum of indices is k. The problem is that if you sum over infinitely many things, you get an infinite sum. And to make sure that that sum is well defined, you have to normally order it. So in this expression, I have to explain for you a bunch of things. So let me actually explain these things. Where the normal ordered product of two operators, this is something which comes from conformal field theory. So this is defined as QA, QB if A is bigger than B, and QB, QA if A is smaller than B. So normally ordering a product of elements is just saying, well, you take these operators and you put them in descending order of their indices. Now this, his delta Tru here is going to be a Chow in S times S. And I will tell you what it is. It's something which people that study Chow groups of K3 surfaces have seen over and over again. So delta TR is equal to delta 2. Let me make a sub where. So there's a lot of wheres here. Where delta T is the smallest diagonal inside ST. So delta 2 is just the diagonal inside S times S. But I mean, of course, it follows from the notation that I will have to subtract two things. So you subtract C1 and C2. I do realize I have to tell you what those are, but let me just finish that formula over the sum of L1I, I should not put my indices up there, times L2I, where the sum goes over dual bases, dual Q bases, Li of A1 of S. All right, I have to recall for you that C is the particular element in Chow 2 of S which we have discussed here. And the indices, well, C1 is just first projection pullback of C, and it's an element in A star of S times S. And analogously, C2 is second projection pullback of C in A star of S times S. So essentially, delta TR is the class of the diagonal corrected by exactly products of classes pulled back from the factors that correspond to the algebraic part of cohomology, essentially. If you think of this thing here as being a 24-dimensional object, which, there is a way in which you can think of that, you're subtracting 2 dimensions here, and you're subtracting as many dimensions here as the Picard rank of the surface. You are left with something of the size of a transcendental rank of the lattice of a surface, and that is why we call it delta TR. All right, so finally I have given for you here a self-contained definition of a certain operator on Hilbert. So what do we do with this operator? Well, we're not the ones who invented this kind of an operator. In general, this kind of operator appeared in the works of Lehn, which I will mention in a sec. But let me start off with an exercise. The exercise is show that the operators LK, show that the LKs satisfy the commutation relations in the Virasoro algebra. The Virasoro algebra relations and I will remind you what these are. So these are the commutation relation which say that the commutator of LK with LK prime is K minus K prime LK plus K prime. So I'm not done yet, but this is like a fundamental form for the commutation relation, as opposed from the Heisenberg algebra relation, which says that the commutator is almost always 0 and sometimes it's a constant. This is a bit more complicated. The commutator is never 0. It is a multiple of an operator in this algebra, and you still have to correct it further by putting here the Kronecker delta when K plus K prime is 0 times a certain number, which may seem odd at first. This 12 here actually plays an important role in conformal field theory, so there's a reason why people historically keep this denominator, times B times the identity. The only thing I have to say here is what B is. So B, this object, is a natural number between 2 and 21, and this is precisely the rank of the transcendental lattice of S. The rank of the transcendental lattice of S. So let me just call this H2 of STR. For the purposes of this talk, the only thing which matters here is that B is a number between 2 and 21. Well, you can prove this relation essentially by taking this definition and using those relations over there, and it's a little bit more complicated because delta TR is not, well, it's not decomposable, but it's not hard to take the natural generalization of this commutation relation, apply it to these operators, and obtain this formula here. So that's why I'm calling it an exercise. And B essentially comes about because the pairing of delta TR, the product of delta TR with itself is B times delta TR or something like that. Anyway, so this is part 1 of the exercise. Part 2 of the exercise is that LK actually commutes with the QK gammas, QK prime. These two types of operators commute for any K, K prime, and any gamma in RS. So that will be nice for our representation theory. All right, I have given you here 3 whole boards of representation theory, and I have not explained yet what this has to do with tautological classes. So I owe you that.
Sorry.
Yes?
For the first relation, do you need to use this relation involving the third?
Nope, but that will come up in a bit. I don't think so. I think all you're doing is taking the product of the diagonal on S times S with itself. You don't do something on S times S times S. But the relation which you mentioned will appear in 1 second. Okay, so here's one of our main technical results. So this theorem goes back to Lehn in cohomology, and we prove it in Chow. This thing is actually a formula for the following operator. So let me introduce some notation. So let gk of gamma between A star Hill and itself It's okay. Well, I mean, I'm doing some grunt work here, so I can do it in silence. So let's give a name for the operator of cup product or intersection product with a tautological class. With the tautological class that, let me recall for you, the notation is pi1 lower star chk of oz times p2 upper star. So these are the tautological classes which play a role in our main theorem. The theorem that Lehn discovered in cohomology and we extend in Chow is a formula for these operators when k is small. So when k is 0 and when k is 1, there's nothing to prove, as you can see on the board. The first interesting case is when k is 2, in which case the formula says that g2 of gamma is equal to minus summation from n is equal to 1 to infinity qn q minus n of delta 2. So it's saying that the operator of multiplication by the first non-trivial tautological class can be expressed in terms of these Nakajima Krasnovsky operators qn and q minus n, and you have to feed inside here the class of the diagonal. Well, I guess times gamma, since there has to be a gamma in the right-hand side. So when I write diagonal times gamma, I mean diagonal times the pullback of gamma from any factor. So you can use any factor. The more interesting one actually is what happens for G3. So G3 of gamma is given by the following formula. And this one is going to be a bit longer. You see, G2 of gamma is a quadratic expression in the Q's. G3 of gamma will be a cubic expression. And the formula will be sum over all n1, n2, and n3 adding up to 0. You have to normally order them because that's what you do in infinite sums. So qn1, qn2, qn3. And inside here you have to feed a class in the in the Chow of a triple product, and that class is delta 3. I mean, since I'm doing K3 surfaces, I could stop here, but this formula actually holds for any surface. So for any surface, you have to correct it by a quadratic expression, which is 1/2 summation n goes from 1 to 1 to infinity, n times qn times q minus n, there's the little gamma here, delta 2 little gamma times c1 of the tangent bundle. So this He1 will not appear, will be 0 in the case of a K3 surface, but this formula here actually holds for Hilbert of S, for Hilbert of S for arbitrary n. So this is called, this property here is called Lehn's formula, or I guess I call it Lehn's formula. You can use it to generalize this, and this is exactly what Li-Qin-Wang did. So the second theorem is Li-Qin-Wang in cohomology, and we in Chow. Actually, Li-Qin-Wang proved more than what I will write here, but I will only write the part of their proof which I need. They give a formula for gk of gamma for arbitrary k, And it is essentially a generalization of this formula over here. So in this formula, G3 is given by some cubic expression in the QNs. You can imagine that, well, in general, you will have here an expression involving a k-fold product of Qs. So you need to sum over all n1 greater than n2 greater than nk. These are integers. And over here you put qn1, qnk, and inside here you have to feed a class in the k. Let me actually call this t, just because everything, the role of this thing was played by t. Here you put the class of the tth diagonal. So this is the class of the smallest diagonal inside the product of t copies of the surface with itself. And of course there are some coefficients which I will not bother writing down, so some integer coefficients. So this is the formula. All right, why do we care about that? It's all nice and good to prove formulas, especially if you're doing representation theory, but why is that useful for us? Well, the corollary of this thing is following. I claim that the operators GQ of gamma, so these are operators, I claim that they lie inside the algebra Heiss times Vir, acting on the Chow of Hilbert schemes. So I realize I have not technically defined this, so Vir is the algebra generated by the operators I call LK, and Heiss is the algebra generated by the operators QK gamma, as k goes over the non-zero integers, and gamma goes over this particularly important subring. His operators are additive in gamma, so you can just take these operators for a Q basis of the ring R of S. Also, these two types of operators commute, so this actually is the product of the algebra. So you can take them, you can think of it as tensor product over Q if you want. So I claim that the operators here can actually be found inside this algebra action. Well, sketch of proof or idea of proof, this uses the fact, which is very, very particular for K3 surfaces, because S is K3, the tth diagonal can always be decomposed. Well, there's a formula decomposing it, decomposed into diagonals for 2, the class C, and various pullbacks under the projection maps from ST to either S or to S times S. And his formula, I think, goes back to the paper of Beauville-Voisin from a number of years ago. So this is the idea of proof. All right, so I'm almost out of time, but now it's time for me to give you the thing I promised. So a proof of our theorem, the theorem which is up on the top board on the right. The top board in the middle. So essentially, our theorem is a statement about tautological classes. But because of this last corollary, you can take this statement about tautological classes and think of it as a statement about an action of a certain algebra, and that algebra happens to be Heisenberg and Virasoro, which, you know, in representation theory, they are considered pretty simple enough algebras, essentially because they have simple enough representation theories. So let's write here proof of our theorem. And let me recall, because I think it was on the board I just erased, the theorem was saying that the cycle map from A star Hilb to cohomology of Hilb is injective on the subring generated by tautological classes of the form pi 1 lower star, CHKOZ, pi 2 upper star. So, because of the corollary, so the corollary implies that it suffices to show that zeta, the cycle map zeta, is injective on a certain submodule. Specifically, this is injective on the submodule of this Heiss times Vir representation. So this submodule is Heiss times Vir, the algebra acting on a particular vector called V0. Let's call this submodule V, and it's going to be a submodule of the entire Chow. Where I have to tell you what V0 is. V0 is a very simple element. It's an arbitrary non-zero element of the Chow of Hilbert 0. Because Hilbert 0 is just a point, the Chow of Hilbert 0 is a single Q. So this V0 is called a vacuum vector in representation theory. I'm just saying, consider the submodule under this Heiss times Vir action generated by the vacuum vector. Because of the corollary, this submodule called V contains the subring generated by tautological classes. So because of that, it suffices to show that zeta is injective on this submodule. So in representation theory, how do you show that a function is injective on a kind of module for a representation? You use Schur's lemma. I mean, I guess, Schur's lemma is probably not something you expect in a talk in Lumini, but it's actually a wonderful fact. So Schur's lemma implies that it suffices to show that V is a simple module. It suffices to show that V is a simple Heiss times Vir module. So for the Heiss part, that's actually a simple exercise. So for Heiss, for the action of the Heisenberg algebra, pretty much, well, all lowest weight modules are simple. I'm not going to say exactly what lowest weight means, but it's immediate to show that this module V is simple for the Heiss part of the action. So his part is kind of trivial, are simple. For Virasoro, it's a little bit less so, so you have to say something. But you can actually say that for Vir, this module V is simple because of the classification of the representation theory of the Virasoro algebra action, because of Feigin-Fuchs classification of Vir submodules, So let me recall for you what Feigin and Fuchs say.
When you say for Vir, V is simple, you mean Vir times V0? Not just
V is, as I defined it, a module for the action of a tensor product of commuting subalgebras.
Yeah.
It's easy to show from that V itself is a tensor product of a Heiss module and a Vir module. And essentially what I'm saying is show that Heiss module is simple and show that Vir module is simple, which implies that her tensor product will be simple for the tensor product action.
Yeah, but I mean, see, you define the V.
This is a big V, sorry.
Yeah. I think maybe you know that V, right, which is the Heiss times Vir V, is not equal to the thing that's simple for Vir, which is just.
No, it's not. So I'm being sketchy here. So I should say, let me not be sketchy. Let me not be sketchy. I apologize because it's the crux of the argument, and it would be a shame to spoil everything at the end.
Once you've admitted that you're being sketchy.
No. It's not something to be proud of. I mean.
Oh, I think you're good.
All right. So V is going to be equal to V Heiss times V Vir. This thing is acted on by Heiss. This thing is acted on by Vir. This thing is simple, which is easy. And this thing is simple because Feigin and Fuchs tell us that lowest weight modules, Vir modules, for B, for the central charge B in the interval 2 to 21. So B, remember, is this important number which appears here, and the representation theory of the Virasoro algebra depends on this number B. Feigin and Fuchs tell us that when B is in this interval, the only place a Vir module can have a submodule, so lowest weight Vir modules, can only have a single possible submodule, a single Vir submodule. And this Vir submodule has to be generated by a very specific element, which is generated by the vector V1, which is nothing but L1 times V0. So, I promised you that this module is simple, but I'm telling you that, it could have a submodule. However, what is V1 in our case? So V1 is L1, and remember at L1, because of the formula, is minus summation n goes from 1 to infinity, Ln plus Qn plus 1, Q minus n delta Tr acting on V0. And I claim that this whole thing is 0 just because Q minus n acting on V0 is always equal to 0. So how do we see that? Well, you can actually see it from this diagram. So Q minus k takes you from the Chow of Hilbert plus k to the Chow of Hilbert. So Q minus k takes you from the Chow of Hilb 0 to the Chow of Hilb minus k, but there's no such thing as Hilb minus k. So it has to be 0. So because of that, Q minus n kills V0, and because of that, L1 kills V0, so V1 is 0, hence this thing here does not have any submodules, hence big V is simple. And this concludes her proof. Thank you very much.